Good morning, everybody. So let's begin today's program, which is the felicitation of the international medalists of the medalists of the International Olympiads of 2024. This program is sponsored by the Infosys Foundation and the TIFR Endowment Fund in collaboration with HBCSE-TIFR. I am Anvesh Mazumdar, the National Coordinator of Science Olympiads in India, and it's my pleasure to welcome you all today. So the actual award function for the medalists will start later in the day at 12. But as has been the tradition since the very first year that we had this program in 2004, that the program is preceded by two scientific talks by eminent scientists. And we are very happy to invite our speakers today, Professor Archana Pai and Professor Siddhesh Kamath. The first talk, the first lecture, will be given by Professor Archana Pai. Professor Archana Pai is a professor at the Department of Physics, IIT Bombay. She obtained her bachelor's from Ruparel College and secured her master's in physics from IIT Bombay. Subsequently, she did a PhD from the Inter-University Center for Astronomy and Astrophysics, IUCA as we know it, in Pune, in gravitational wave astronomy. After her PhD, she was a postdoctoral fellow at several renowned international groups. She was a Henri Poincaré fellow at the Observatory of Nice, France, an INFN fellow at the University of Rome, and a postdoctoral fellow at the Albert Einstein Institute in Germany. Her broad research interests are developing signal detection algorithms for gravitational wave transients, multi-messenger astronomy, and testing Einstein's theory against observations. She is the chair of the LIGO India Scientific Collaboration, which is a multinational pan-India group of scientists who work with LIGO Scientific Collaboration. She has received several recognitions, such as the NR Sen Young Scientist Award, the Peraya Foundation Lecture Award, and the Vaidya Raichaudhuri Lecture Award. And she also shared the special Breakthrough Prize in Fundamental Physics, the Gruber Prize in Cosmology with the LIGO Scientific Collaboration. Welcome, Professor Pai. Over to you.
So thank you very much. I'm very happy to be here. And first of all, congratulations to all the medalists. I'm sure you're going to do well in whichever career you choose later on. All right. So, so the talk which I'm going to give today, I'm audible, right? Everybody can. Yeah, okay. Is the decade of gravitational wave astronomy. So this is a new branch of astronomy, and I thought maybe some of you are already familiar with it, and those who are not familiar with it, I'll just give you a glimpse of the field, which just began 10 years ago. So we are going to celebrate in next year the first discovery of gravitational waves, which happened in 2015. All right. So let's begin. So all of you are familiar with electromagnetic spectrum, right? It goes right from, we talk about from, let's say, gamma rays to radio. And in all of the universe which we observe so far is primarily in the electromagnetic band, looking at various phenomena at various wavelengths and various sort of, physical, astrophysical phenomena. So the same object we observe in different bands, and when we observe in different electromagnetic bands, it carries a lot of information about the source, right? Because it carries different information, regarding scattering, absorption, right? So now, why did it go blank? Excuse me. Yeah. All right, so this is the glimpse of the cosmic objects which we have observed so far. So we have active galaxies with, at the center, a lot of activities happening. We know that there are clusters of galaxies, stars. We know towards the end of the stellar evolution, you see supernova explosion, which we can observe. and of course our sun. So there is a large variety of sources or phenomena which happens in our universe, and this is all we have observed using the electromagnetic band. However, there are lots of questions which are still open, which we have not really, we have some understanding of that, but not everything. So for example, how, this is about our universe, how our universe has began, or how basically when we talk about, let's say, the matter in the universe, why is it lumpy? We know a little bit, we have, the Einstein's theory has been sort of successful in flying colors. However, there are indications which are questioning the theory of Einstein's relativity. So there are all these open questions, and we expect that the new observational window, namely gravitational wave astronomy, might be able to give some clues to some of these questions. Okay? So now let's begin with what are gravitational waves. Okay, so so I think all of you are familiar with Galileo, right? And this famous experiment, you can sort of see that, Galileo is instructing them to drop balls of, different material, different size, different mass from this Tower of Pisa. And essentially this laid down the foundation of equivalence principle, namely like independent of the masses and material, right? Both the balls come together at the same time, okay? Later on, Einstein essentially formalized this idea, and he actually put together the mathematical structure or foundation. And the gist of it, I'm not going to go into details, this is not for that, but the gist of the theory is that if you consider sun, okay, and let's say this is sun and this is earth, then any massive body essentially creates a sort of geometry. It perturbs the geometry around it, okay, which is depicted in this sort of sheet, curved sheet, which you can see here with some, curvature. And if you take smaller object, then they move around this object essentially following the geometry. So for example, if you take, let's say, a rubber sheet, right, drop a ball at the center of the rubber sheet, that will create some, drop, whatever, the whole surface will change because of the weight. And now if you take a small ball and you just keep it on the sheet, then the way the small ball moves, okay, is exactly how our Earth is moving around the sun. So Einstein essentially completely gave a new way of looking at gravity, right? So earlier Newton said that, okay, you have the gravitational force is inverse square law, proportional to the product of masses, etc., etc. However, with Einstein, and of course because of that there were lots of other issues. For example, if sun disappears, then according to Newton's law, you will see the effect immediately, right? There is no time taken by this interaction to propagate in Newton's gravity, okay? But that doesn't happen in reality, okay? We know that it takes something like, roughly 8 minutes for light to travel from sun to us. Okay, as a result, if the sun disappears, then we'll know in roughly 8 minutes that the sun has disappeared. So Einstein's theory essentially takes care of all these things in its, in the way the theory is. And this picture essentially revolutionized our way of looking at gravity. Now, any new theory always has their own prediction. So any theory we sort of confirm that, okay, this is the one which follows, nature follows. One is if it sort of, all the earlier predictions, all the earlier observations, let's say the theory can explain. And also it predicts some new sort of predictions, and it proposes what are the ways to observe that, okay? So there are several predictions of Einstein's theory. So namely, what it says is, so there was this big puzzle which was this Mercury's orbit. So the Mercury's orbit never really closes, right? It's a closest, we know that it's a closest planet to the sun, and as a result the gravity is strongest compared to all the other planets, right? And with Einstein's GR, we could explain this orbit of Mercury because of this new picture, there is an extra term which gets added and with which you can actually explain why the Mercury's orbit doesn't close. Okay? Similarly, there was another sort of prediction which is called as a bending of light. So let's say this is a real star's position. There is a big star, a big white dwarf sitting in front. Okay? Just because of this white dwarf, it will alter this geometry. And because of that, the real position is here, but the light will not come straight, but it will bend. And it will bend and come here. So as a result, the observed star's position, you will infer it as here, whereas the actual real position is somewhere else. Okay? So this is called as a bending of light. It's something like how, the big objects or big stars, they behave like lens, like an optical lens, like how when you have a lens, then the light bends, right? So that is what was another prediction, and this was confirmed pretty much immediately after the theory was proposed by Einstein. That was in 1919. There was a solar eclipse, and in the solar eclipse, you know that the solar, the limb gets completely covered, right? And as a result, you could actually observe the stars which are behind, and they could actually see this change in the position of the star because of the sun. Okay, so this was sort of explained pretty much immediately. There is a little pointer for all of you. I think there is a movie called as Einstein and Eddington, right? So the Eddington was the one who, geared this whole experiment. And if you have not watched this movie, I strongly recommend you to watch this movie. It's a very beautiful movie because the whole thing is set up during the World War time. And it actually tells you, during the World War, the whole atmosphere, and then how Einstein sort of maneuvered the theory and the whole, historical. It gives you a historical perspective to this experiment. All right. So now the one of the prediction of Einstein's relativity is gravitational waves. Okay. So I'm just going to play a little movie for you, so that you get a picture. So basically these two objects, they will have its own perturbation of this matrix, and as they sort of move around, right, the geometry around them will follow the motion in terms of these waves which are going away from the source, okay, and that can be observed by us. Okay, so this is what is the gravitational waves, and this was predicted by Einstein. However, so this is another sort of way of looking at it. You can think about it as a pond, for example, right? So if you throw a stone on the surface of the pond, then you see that the ripples sort of travel away from the source, right? So it's quite similar. Now, gravitational waves are, it has certain properties. Okay, so it travels with speed of light. They are transverse in nature, right? It is basically perpendicular to the, all the perturbations are happening perpendicular to the direction of propagation, like how happens the electromagnetic waves. Okay, so these are basically some of the properties of gravitational waves. Now the question is, though he predicted this, essentially if you look at the amplitude of gravitational waves, I think this is the only equation I have put it, right? It essentially, so this is the amplitude, it goes as 1 over the distance and 1 over c to the power 4, c is the speed of light. Okay, so now this whole constant g by c to the power 4, it makes gravitational wave extremely weak. Okay, so it is a very weak waves, and because of which it was very difficult to detect these waves. So though it was predicted long back, almost like 100 years ago, it took a long time to really detect them. So for example, if you take these two stars which are going around each other, okay, and I put these two stars maybe in our, somewhere with some period of 8 hours, and somewhere in, let's say, in our galaxy or outside galaxy, then I'm just giving you a typical number of this amplitude. So this amplitude is extremely tiny. It is roughly 10 to the power minus 21. Now what is this 10 to the power minus, what is this amplitude? This amplitude essentially translates it into a strain produced if the gravitational waves are incident. So it is delta L by L. So which basically means that if you have L is equal to, let's say, 1 meter, then you should devise instruments which can measure the change in L to be roughly of the order of 10 to the power minus 21 meters. Okay, so it's an extremely tiny number. I've also given some number if you have some terrestrial source, because according to Einstein, anything which sort of produces asymmetrical motion. Okay, so for example, if you have a rod and you let it spin, okay, take some rod of maybe 10 meters with some frequency, 10 hertz, and very massive rod, then that will also produce gravitational waves. So there are various sources of gravitational waves in and around us. However, the strain which they produce is extremely tiny that we cannot, they're basically unnoticeable. You cannot really, So then if that is the case, then how do you really detect these waves, right? And Einstein was very skeptical about it. He thought that we will never be able to detect them. However, just because if you have, let's say, sources which are astrophysical, okay, then just because of the compactness of the sources, there is a potential, there was a potential to detect these gravitational waves. Okay, so basically it depends on the compactness of an object. So compactness is given by the mass of the object divided by the size of the object, okay, and this is a dimensionless number, so you can sort of make it dimensionless by multiplying by g and dividing by c square. Okay, you can write it equivalent to square of the escape velocity divided by the square of the speed of light. Okay, so now the escape velocity of the black holes is c, right? So as a result, your compactness parameter is essentially 1. So that's the most compact object, and as a result, that is the one which is the candidate of gravitational waves, if at all, if we can detect them. All right. Okay, so now there are this zoo of astrophysical sources of gravitational waves. So basically merging objects, compact objects. If you have, let's say, a black hole and then there is something is accreting mass, right? Or if you have a supernova explosion, if you have a neutron star, okay, which is made up of only neutrons and protons, and if it is sort of having some asymmetry on it and it starts spinning, that will produce gravitational waves. If you have, let's say, merging galaxies, then the centers of the galaxies harbor supermassive black hole, and they can actually form a binary system and they can produce gravitational waves. So there are lots of sources which can produce gravitational waves. Right, so now this is about just giving the glimpse of gravitational waves, gravitational sources. So now towards the gravitational wave astronomy, like how do you really detect them, have we detected them, and so on and so forth. Okay, so now here is a little video, so you can look at this. So imagine that the waves are incident along the axis of the cylinder, okay. Then as the wave propagates, the cylinder, okay, will get deformed based on the frequency of the waves. Okay, you can see that if you look at the cross section, then it will essentially get elongated, and then alternatively it will get elongated and along the two axes, right? So this is how the waves will impact, right, when they are incident. Though that impact or the strain is extremely tiny. I mean, here is just for the visual effect, we have just amplified this whole thing, right? So this is what will happen. So you can see there, if you have a ring of particles. Right, so now based on that, there was this proposal of LIGO Interferometric Gravitational Wave Observatory, what we call it as LIGO. It was proposed by 4 scientists, right? And the whole idea was that you can use a Michelson interferometer. Okay, so you use the principle of interferometry, okay, where you take your laser beam. There is a video which we have, which I can play it for you. So using the Michelson interferometer, you can interfere the light beams, and then if there is a change in the length, then it can be observed in terms of the interference, in terms of the intensity of light. Okay? So there is a history of gravitational wave astronomy. So it was proposed, I mean, Einstein gave in 1916, and then there were all these prototype instruments. The LIGO started in 1997. All the way, the discovery happened in 2015, and now we are currently having our 4th observation run of LIGO, Virgo, Kagra. So I'll explain all this later, but the whole point of showing this slide is that it all began in 1916, and we are almost like 100 years after that. So for anything, it takes a long time. Okay, so it really takes really long time in this case. So for example, the scientist who proposed this, so of course he and they got the Nobel Prize very recently, but they have spent almost their entire life, okay, on this. Of course it was worth it. Alright, so here is the little video where you can see, so this is the Michelson setup. This is a laser. There is a beam splitter which splits the beam in 2 parts. There are 2 mirrors which will reflect the light, and then it will be combined here. Okay? And as the gravitational waves are incident, this arm length will change, and as a result your interference will change. Okay? So this is the basic principle. So I'll play a video for you. So you can see this, the laser is coming back. Now imagine that because of gravitational waves, this get altered, and as a result you will see a little zoomed video where you can see how the laser beam is sort of getting reflected and then eventually combines, and then you have, there is the interference which you collect at the photodiode where you collect the intensity, and as the gravitational waves are incident, then this is going to change, and as this changes, then you will see here how the intensity of the light essentially changes. Okay? So the goal is you devise something like this, and then you try to measure or sense the intensity of this light, and then using this you can infer what age must have been of the incoming source. Okay? Alright. So now, but as you notice here, this delta L is h times L. So higher is the length, then you can actually measure longer, more strain, more delta L, and as a result your effect here would be more detectable because h is not in your hand, it's something given by the source, right? So the whole game is to have longer arm lengths, okay, and to get this sort of detectability, right? So now look at this LIGO experiment. So these are basically 2 LIGO detectors, both in US, one in Hanford, Washington, and the Livingston, Louisiana. They are 4 kilometer arm length. So you imagine the whole setup is, so here is a beam splitter, and then there is a laser, the laser goes here, gets reflected back and then collected here. Okay, so it is a 4 kilometer arm length detector, okay, and which has been sort of running for past few years now. Alright, so advanced LIGO detectors, they are absolutely, so, and we have detected gravitational waves, okay. So it is an engineering and technological marvel. We have been able to achieve the strain sensitivity of roughly 10 to the power minus 23 now. Okay, so these are 2 interferometers with 4 kilometer vacuum chambers, 3000 kilometer apart, operating together to measure a motion of, let's say, 10,000 times smaller than the atomic nucleus caused due to the violent events in our universe located at billions and millions of light years away. Okay, so this is like an absolute achievement. These are a few pictures of this advanced LIGO. So if anybody is interested to know more about the technology, we can talk about it later. I'm not going to spend right now this thing, but that, in order to achieve that, there were lots of technological, advancements, and also special techniques have been used in order to sort of make this happen. Okay? So this is sort of the vacuum. These are the suspensions. You need to suspend the interferometer. It is not a simple optics. Okay, so you need things to suspend. So actually the suspension is a very simple way to filter. Okay, so for example, I'll just give you a little demo. So consider this as a suspension. Okay, and imagine this is a mirror. Okay, now when typically we are looking at the frequencies where even if, and we are trying to sense very tiny changes in length, right? So even if, let's say, objects are moving around, let's say vehicles are passing by or people are moving, right? Then this is going to get affected. All right? So now how do you make it sort of, immune to that, or how do you sort of filter out? So the pendulum, simple pendulum is a classic suspension. Okay, so I'll give you a demo. Okay, so now look at it, look at the motion of this. Okay, I'm going to excite this. Okay, now look at the center of mass, it remains same, right? Now I'm going to excite it, right? Right? So now the center of mass is moving, right? So basically what did you learn? So if you have a high frequencies, so this was a high frequency, this is a low frequency, right? So the high frequencies, right, does not really affect the motion of the pendulum. Okay, so now I had just one suspension. So now if you have, let's say, multiple suspensions, okay, then you can actually achieve whatever frequency band which you are interested in, okay, by carefully designing the suspensions, and that's what is done in LIGO. Okay, so these are the suspensions, these are LIGO suspensions. There are 4 stages of suspensions which are used, okay, to achieve the frequency band which we are interested in. Okay, so this is the optical layout. So you have a laser. This was during the discovery. There's a beam splitter which splits the beam, comes back, and so on and so forth. But now it is not just a simple mirror here. There is one more test mass has been added, which creates something called as an optical cavity. So the interesting thing is of this cavity is it reflects the light multiple times inside the cavity. Okay. So when you multiply many times it reflects, then essentially you are increasing effectively the arm length of the interferometer. So now it's not just a 4 kilometer, but it's depending upon the the number of times, the round trip of the laser, you can multiply by that, and that will give you effectively a longer arm length, which is what we are interested in. Okay, so this is one of the technique which we use, which is you put an optical cavity, makes the light beam reflect several times. All right, and with this we have achieved now. So you can consider this y-axis to be h. So you can see that we have achieved something like 10 to the power minus 23, better than 10 to the power minus 23. Okay. All right. So now with this we have moved towards the discovery. So I'm going to play another video for you. Okay, so what you have to see here, so in the second part you will hear something like okay, let's play again. Not here now. You hear that? Okay, so this is the sound of the real event which we obtained. Okay, this was in September 2015. So both the detectors essentially observed this event, okay, where you see this, right? Okay. So now what is this? So let's try to understand this picture. So this is a time and this is a frequency. So as the time progresses, the frequency goes up, and the color or the brightness essentially characterizes the total intensity at that time and frequency. Okay. So essentially this was the feature of this event. We call it as a chirp, as the way the birds chirp, right? So the birds in the morning time, you hear these birds chirping, it's pretty much same. So we call this as a gravitational wave chirp. And this was observed in coincidence in both the detectors, giving a clear indication that this was this is something coming of astrophysical nature and not of the local origin. All right. So this event, when we did all the calculation, it appeared that it came long back, okay, when on Earth essentially we were somewhere between these two eras where there is a multicellular life was forming on the Earth, when the event started long back in the universe and came and reached our Earth on 14 September 2015, 10 years back. All right. And what was the event? It was actually merger of two black holes. So you can see this. So there are two black holes which are merging. They are in binary orbit. They are in orbit. As they following the Einstein's theory, they essentially emit gravitational waves. So they leave. There is some energy is lost. Hence they come close to each other, and then they finally merge. That's where you hear that whip up. And this is a signal which it will produce, and the final black hole tries to settle itself, and this is the final settling phase. So you have this inspiral phase which is a chirp, and then you have final merger, and then you have this settling phase. Okay. So this was a discovery. The discovery was quite spectacular because the event was very bright. I just showed you. The final, we estimated what are the masses of this system. So it was 36 and 29, roughly 30 solar mass black hole system located at roughly 500 megaparsec distance. So it's quite, it's quite far away. And the final black hole was something 62 solar mass. So whatever was this 3 solar mass energy was emitted in gravitational. So it was a huge really event. Okay. Which sort of translates to so many times basically what we get from sun. Okay, right? So the discovery was there was a lot of publicity of the discovery, and subsequently there was the in principle approval of LIGO India project, okay, which happened in 2015. In 2017, pretty much 2 years after the discovery, okay, the Nobel Prize was announced to the physics, and this is Rainer Weiss, the young Rainer Weiss, which I showed you. This is Kip Thorne, both of them very young, and they received the Nobel Prize. The discovery was very unique because this was the first direct detection of gravitational waves. It was the first direct observation of black hole merger event, okay, and also indication of black holes which might be a larger black holes in our universe, as compared to, let's say, 10 solar mass black holes, because we were not aware of it that these such black holes exist. Okay. All right. So now since then, these are two LIGO detectors. There is a Virgo detector in Italy, which is just outskirts of Pisa. There is a Japanese detector which is getting ready, and this is the LIGO India detector, which will be coming up very soon. Since then, we have observed many black hole mergers. So in 10 years now, we might be almost hitting, like, I don't know, 200, 250. Our observation run is going on. So all this, this line which you see here. So if you take any line, let's say this line, then these are the two primary objects merging and giving this final object. Like that, there are many of them. This is the summary from our 3 observation runs, which total we have 100 such compact binary mergers. All right. So now I'm just going to spend maybe next 5 to 7 minutes on 2 besides the first discovery, we also solved lots of puzzles in astronomy. So I'm just going to highlight 2 of them. Okay, so the first one is short gamma ray burst puzzle, which was solved. So earlier in gamma ray astronomy, people have seen gamma ray burst. It's a small, burst of signals observed in a very short time, like seconds. And people didn't know, these, gamma ray bursts, what are the progenitors? What is it that they're forming these bursts? This was an open puzzle for a long time, and people thought that maybe it's a merger of neutron stars might be giving rise to such such bursts. And then in 2017, we observed a very unique event. This was the chirp track which we have observed in our LIGO data, and immediately, almost like 1.7 seconds later, there was a short gamma ray burst observed in the Fermi satellite in the gamma ray window. Okay, so that essentially told the community that maybe these two are coming from the same source, and subsequent analysis essentially showed that they are basically from the same source, and the source is the binary neutron star merger, which eventually gives a short gamma ray burst. Okay, and this was the beginning of the era what we call it as a multi-messenger astronomy. So it is not just the astronomy which we do between different electromagnetic windows, but now there is astronomy which we are going to do between the electromagnetic window and gravitational wave window, because these two windows are going to carry completely different information and going to tell us much more about the source. Okay, so this was the confirmation of binary neutron stars as the progenitors of short gamma ray burst. I'm going to play a video how this event must have happened. Okay, so this is the video. You can see the two neutron stars in a binary orbit. They are going to produce gravitational waves, which you can see here, and then finally they sort of merge and forms a gamma ray burst, which you see here, which was observed. Subsequently, this burst also gives rise to kilonova, because these are like neutrons, lots of neutrons are getting released, and that essentially helps in synthesizing the heavier elements in our nature. Okay, it also produces something called as afterglow, because it is sort of giving power to the medium around, which gives rise to afterglow in different electromagnetic bands. So this event was quite spectacular in that sense. We learned a lot about it, namely we learned about the possible formation of heavier element because of this neutron emission and R process nucleosynthesis. We also learned about the cosmology from this event, because this event was, we could identify the event in a particular galaxy, and if you know from where this event has come, then you can use this information to even understand how the expansion of the universe, which is characterized by the Hubble's constant. So we actually measured the Hubble's constant using this event. So it was quite rich in science, this event. Okay, so that is about 17/17, glimpse of that. The next one, which I am going to focus on, what is called as the intermediate mass black hole discovery. Okay, so this was another discovery which was quite spectacular. So now in black holes, we talk about two types of black holes. So we talk about low mass black holes, roughly like our solar mass, maybe higher, roughly less than 100 solar mass maybe. And then we talk about heavier black holes, which are sitting in the center of our galaxy. Okay, so our whole galaxy, it's like an engine of our galaxy. So because of that black hole which is sitting at the center, it sort of drives the galaxy. Many of these spiral galaxies, there is a central engine which is a supermassive black hole. Now the question is how these supermassive black holes are formed to begin with. Okay, it's an open question, we don't know. Okay, and for a long time people have been looking at black holes which fall between these two black hole ranges, what we call it as intermediate mass black holes, which are maybe around 1000 solar mass or more than that. And there is sort of theory which what people say is that maybe there are two black holes form a bigger black hole, and that black hole merges with another black hole and then keeps forming bigger and bigger black holes, and maybe eventually that's why you get this very massive black holes. Okay, so this is called as sort of, if you have a very dense environment like clusters, globular clusters, or maybe centers of our galaxy which is very densely packed with lots of stars and heavier stars basically, that eventually such a phenomena might be happening. So this is something which people think, okay, and people are still looking for evidences of such theoretical sort of speculations. So now this event which we observed, which was pretty massive event, it was 85 solar mass and 66 solar mass coming together, merging and forming a black hole which forms in the intermediate mass black hole range. Okay, so this was 142 solar mass. So this was the first confident intermediate mass black hole discovered in astronomy. There are sort of candidates in the electromagnetic astronomy, but nothing was very conclusive. And the interesting thing is these black holes, which are the ones which make this bigger one, it's not very clear how these black holes are formed, okay, because just from the star, stellar evolution, like the way our understanding is that when a massive star is towards the end of its life cycle, it becomes black hole. Using that, mechanism, you cannot form black holes of this mass. So as a result, people think that maybe there was another merger of some old binary which might have merged and formed this, and maybe this also is formed by the previous merger and formed this, and then and now they have merged and formed this. So this is the first sort of indirect evidence of this hierarchical scenario which I was talking about, that two small black holes merging into big one, then that forms a binary with something and forms, and so on and so forth. Okay, so this is, and hence this event was quite spectacular, besides the fact that it is the first IMBH discovered, but it also opened up all these new questions about how the black holes are formed in our universe to begin with. So yeah, so this was the two discoveries. Now let's just spend a couple of minutes on LIGO India. So the LIGO India project it's going to be the third LIGO in India. It is going to be in Maharashtra, in Hingoli district, in Aundha. This is the location. So this is about the approval. Now what is the science? I mean, why this LIGO India is interesting? Okay, so it's interesting because of the following reason. So if you take, let's say, the two LIGO detectors which I have shown here, okay, on our map, and the Indian detector is here. So if you look at the baseline, it is 39 milliseconds, which is the longest baseline. So this is the light travel time from this point to this point. Okay, so that is the longest one, because if you roughly see, India and US is almost like opposite sides of our globe, and that helps in localizing the source. Okay, it's like the standard triangulation method, like, because the time delay, the longer is the time delay, you can localize the source better basically. Okay, so for example, if you take the sky map, okay, and if I put all these violet bananas are essentially the localization using just two LIGO detectors. But now if you add the Indian detector to this, then you see all this blue ellipse, and you can see that the blue ellipse is very small in size compared to this banana. So which basically means I can pinpoint the source better. So in gravitational wave astronomy, pinpointing is always an issue because it's not a telescope which you can just point, okay, because we see from everywhere. Advantage, because you see a lot. Okay, disadvantage, you cannot pinpoint. Okay, so you have to use techniques to pinpoint, and more the detectors, the wider is there a separation, you can pinpoint better. So that way LIGO India has sort of promise. Future, so these are the different observation runs. We are somewhere here. This is the fourth observation run of the gravitational wave global network. So we always work in cooperation, we don't compete, okay, because we want everybody together to pinpoint. Okay, so this is the fourth observation run, we are somewhere here, and then in the fifth observation run we will see much deeper. Hopefully LIGO India will come somewhere here, will start operating something like 2030 or maybe a bit later. Even more further in future, so there are future plans where maybe some of you can actually contribute. Okay, so the future is, there is going to be underground gravitational wave observatory. This is called as the Einstein telescope. There is a similar plan of Cosmic Explorer in US. So this is European plan, where they're going to put a triangle underground of maybe 40-kilometer arm length, okay, and which will observe things even more. There is another plan of NASA and ESA joint mission. This is called as LISA. It's a laser interferometric space antenna, where there will be 3 satellites in the triangular configuration, okay, just trailing the Earth, going around Sun, okay, and this is going to be few million arm length kilometer, okay, that's going to be a big one. The goal of this is, the longer the arm length, you can see the smaller frequencies. So with that, you will see more complementary science. So gravitational wave astronomy just beginning now. We are 10-year-old. We have already observed more than 150, 200 events, and we expect now the whole thing to sort of explode in next 10 years. So with that, I'm just going to stop. So these are some of the questions which we hope to answer, besides the question which I showed you at the beginning. This is a group, gravitational wave group at IIT Bombay. We are part of the LIGO scientific collaboration, and we work towards bringing out science from LIGO data. Thank you very much.
Thank you, Professor Pai, for the wonderful lecture. So time for some questions maybe. So if you have a question, please raise your hand. Somebody has to start. Yeah.
You mentioned that you have observed a few hundred black hole mergers.
Yes.
In the past
10 years.
10 years.
Yeah.
So was it some breakthrough in 2015 that allowed the first?
Yes. So yeah, exactly. So at 2015, okay. So I think I don't have that plot. So as I showed you, we could achieve. Yeah, I think here, right? We could achieve this sensitivity, which was h of 10 to the power minus 23. So before that, the detector. So basically, what happens is this is a kilometer arm length interferometry, right? This is all suspended. So it happens in stages. So we essentially initially in early 2000 we took science run, where the sensitivity was around 10 to the power minus 18 or something, and then you have several science runs. Then you improve. Then you increase the laser power. So it happens in various stages. Yeah, it happens in various stages, exactly. So when we achieve this level, that's where we have started seeing. So now, and with each observation run, we improve. So this floor comes down, and as the floor comes down, and as the lower frequency, so you improve the suspension, then you start seeing more lower frequency. Then you see longer signal, so that gives you, higher signal to noise ratio. So we see much deeper in the universe. So now we are in fact, the current observation run, which started in 2023, this is a longer one. It's still going on. So we will observe till next year, mid next year, roughly. And in that observation run, we have seen almost the same number of events so far as we saw in the first 3 observation runs. So this number really grows up because the h goes as 1 over r. So if you improve this a little bit, then you are probing the distance that much, and the volume goes as a cube. So that because of that cube factor, you improve. Even if you make a small improvement, you really improve a lot. So that's the advantage of gravitational astronomy compared to electromagnetic. Because in the electromagnetic, you essentially observe the power. Here we observe the amplitude. So there it goes as 1 over r square, here it goes as 1 over r. So that 1 over r actually allows us to look deeper. Yes, look deeper, and also, hence the volume is, yeah.
Thank you.
More questions? Yeah.
Why does the sensitivity drop at certain values?
Why is it like a bucket?
No. Like there are some peaks.
Yeah, so those peaks are essentially, they are fundamental peaks of suspension, for example. Yeah, so there are resonance, and then there are multiple of that. Okay, we also see power lines. Okay, so 50 hertz, and so this is in US. So ours is 60 hertz, right? That is 50 hertz. So you see 50 hertz and the multiples, harmonics of. You also see coupling between. See, because this whole thing is a very complex instrument. I did not talk about it because, I mean, it's very difficult to explain at this thing. We can talk about it later if you're interested. So there is this, there is a vacuum, right? And then essentially everything is suspended. It has a 4-stage suspension. So each stage has its own oscillations, right? So you have this oscillation, you have this oscillation, right? So you have 6 modes of oscillation into 4, so 24. So you have to essentially control all of them. So there is a feedback loops are on each of these mode in order to make sure that the interferometer is at the working point, whatever you want. Okay? So because of which often there are couplings between the subsystems which show up, which you see as lines. Okay, so it may not be just the harmonics, but there might be also coupling because of which you see, the sum of the 2 frequencies or, subtraction of the 2 frequencies and things like that.
So essentially it's like resonances, so the sensitivity drops because it excites a lot.
Yeah, exactly. Yeah, exactly. So the goal is, as long as we know what they are, we are fine, because then we know it. If we don't know, then that is where the whole hunt goes on to try to figure it out, what is it, because, yeah.
Yeah.
Excellent talk, madam.
Thank you. Yeah.
And I remember when the team visited Ministry of Earth Sciences for related to LIGO experiment. So it's really excellent talk and outcome. Only one this, thing, observation, which I, that this, when we are talking of noise,
Yes.
maybe, that our Mother Earth is so, that is full of still many of unknowns.
Yes.
So when plate tectonics, they keep on taking place, and earthquake events, that they keep on, that continuously something they
happening.
Keep on going.
Yeah, seismic activity.
So maybe that, are they part of this noise, or, that?
So if there is any seismic, big seismic activity, then it shows up. Because it's the low frequency, it all depends at the low frequency. So the band is between 20 hertz to roughly 1 kilohertz, 1.5 kilohertz or something like that. So if there is any seismic activity, it gets captured.
And
generally.
second thing is that quite
and that is an issue actually, because recently when there was an earthquake in Japan, so that really affected Kagra, the Japanese detector, because so in fact we always used to say that I think the Japanese people got interested maybe because there are so many.
And now all country India.
Yeah. So it is.
Maybe we will get some solution out of that related one also. That's what that. Okay.
Yeah.
Thank you.
More questions? Yeah.
This question is not about the LIGO detectors that have already, the gravitational wave detectors that have already been built, but at the end you said that the plans for a space detector that will be 1 million kilometers, which is 1/100 of an AU. So in that case, how do we ensure that the distance remains more or less constant between?
Very good question. Yeah. So I think it is a challenge because it's very important.
Yeah, because like the sensitivity would have to be like that of a proton width.
Yes. Yeah.
Across an entire.
No. So I think it's basically the LISA detector. I should just show you that. So the LISA detector, the idea is not Michelson. I mean, it's not interferometry. I should just take this. So the 3 satellites are going to have their own lasers on board. Okay, let's see. Yeah, here. Okay, so basically so there will be 3 satellites. Okay, it's very important to keep the satellites. Such stable in such that the separation between them is something which we can. Okay, so let me first tell you how the whole working principle of this detector is. So there will be 2 lasers on board. Okay, each laser is going to send the laser beam to the other arm. So you're sending laser on this will send a beam here, from here send a beam here. Okay. It will beat with the onboard laser, so there won't be any reflection or anything. So it will beat with the onboard laser and create a Doppler data stream. Okay, so you have 6 Doppler data streams. Okay, and with these Doppler data streams, we will construct the interferometry in our computer. Okay, so you will basically make Michelson, different configurations of detectors, okay, by adding appropriate delay. So you add as a delay operator, you add a delay with the knowledge of how much is the separation between them. Okay, so in order to do that, okay, you need to know the separation between the 2 up to a particular accuracy. Okay, so that is what needs to be done. You need not know it very accurately. See, because it all depends on what is the frequency band in which you are working. Okay, so within that frequency band, whatever is the requirement of the accuracy, within that you have to do it. Okay, right. So that is what. Now there is other issues. You have to also make the satellite should be drag free, because there will be other disturbances. Okay, so this drag-free technology has already been tested. So there was a LISA Pathfinder mission in 2015 around the same time. Okay, and which actually tested the drag-free technology. Okay, and that was a big success. I mean, they demonstrated that technologically you can achieve this much better than whatever is LISA's requirement. Okay. So that is the thing. So this is basically this drag free, and then this what we call it as a time delay interferometry. It's not a Michelson interferometry. It's a time delay interferometry where you do you apply the delays. It's a fantastic thing. You apply the delays in your computer. So in your computer you are devising all possible interferometers, and you do everything with your computers.
So this being a 2-dimensional thing, will it be enough to pinpoint the location as well, or will we need 2 of these?
Very good question. So the pinpointing here, what happens is the following. So just sort of do a little bit of rewinding. LISA is going to observe not in our audible band. So the LIGO observes from 20 Hz to 1 kHz. LISA will observe from 0.1 millihertz to a hertz. So it's a low frequency. So now if you are measuring low frequency, you will have longer signals, because you will observe the longer in-spiral phase. Because now what we observe is when the signal enters 20 Hz till the 2 stars, black holes merge. But now you are going below the frequency. That means you will observe the previous phase of the same signal. Okay? And it stays for a longer time. It spends more time when the separation of the 2 stars is larger. So as a result, you will see longer signals, longer than what we observe now. So now if you observe longer signal, then the LISA would be going around the sun. So it will also, you have to take into account all the Doppler modulation. But at the same time, you can divide the data into different parts and localize, because the same signal you might see when the LISA goes somewhere else. So basically the same data will have that information. So you don't need more detectors. You
This actually raises one more question.
Yes, I think I hope it's okay.
This will be the final question.
Yes, yes.
Because we'll be going in different parts, like let's say with respect to the sun, we'll be at some
Correct.
1 or 2 degrees apart.
Yeah, whatever.
The sun itself may not have a uniform gravitational field.
Yeah, so I think that
Will it be affecting enough within the frequency
So that
range?
in that inertial, what I told you, that drag-free technology,
okay, drag-free
that
means,
already takes
okay,
into
fine,
account
fine,
all
fine.
the effects. Solar wind, it takes into account lots of things.
Okay. Any more questions? Okay, if not, let's thank Professor Pai
Thanks a
again.
lot. And all the best.
Thank you. Before we move on to the next talk, we'll take a 2-minute break to just set the stage for the next one.